For our force of motion topic, we built a catapult, and for one of the things discussed, we did velocity. The time it takes an object to move from one position to another is referred to as velocity. Because velocity is a measure of position, it also refers to direction objects travel. This means that if an object travels backwards from its starting point, it is said to have negative velocity. For the catapult, we wanted to have as large a velocity as we could on the projectile in a positive direction. The catapult allows a projectile to travel a large distance in a short amount of time, giving it a high velocity.
Our second topic we talked about was acceleration. Acceleration is the increase or decrease in the velocity of an object over time. Acceleration can also be referred to as change in velocity over time. For our catapult, we wanted to have as much positive acceleration on the projectile as we could to achieve a higher velocity. The higher velocity of the projectile, the further it traveled.
We also wanted to talk about Newton's three laws. Newton's first law of motion: an object at rest will remain at rest until a force acts upon it, and an object in motion will remain in motion at the same speed until acted on by other forces. This basically means that objects will continue to do what they were already doing until acted on by other forces. This is because all objects with mass have inertia, which are objects' resistances to change. When the projectile is stationary, it remains so until the catapult launches it. It then travels forward in the same direction until gravity and air resistance slow down the projectile to an eventual stop. The more massive an object is, the more inertia it will have, making it resist even more change. This means that even though more massive objects are harder to get moving, they can continue doing so for longer. This means that having a more massive projectile has no bearing on distance in terms of Newton's first law of motion.
Newton's second law of motion states that the more massive an object is, the less acceleration it will experience. This can be written as force divided by mass equals acceleration. The more massive an object is, the more inertia it has, meaning it will resist change and movement more, which is why it will accelerate less. Newton's second law is another reason to reduce the mass of the projectile as much as possible. So we only use what we needed to reduce excess mass. This allowed our projectile to accelerate more and therefore achieve a higher velocity, which allowed us to achieve a greater distance of our projectile.
Newton's third law of motion states that beginning force is equal and opposite to that of the resulting force. The pulling back of the projectile is the beginning force, and the forward launch of the projectile is the resulting force.
There are two types of energy in our catapult: potential and kinetic. The rope connected to the PVC is pulled back and held in place as the projectile sits still. Potential energy is stored in the tension of the rope. There's also potential energy in the projectile as it sits, waiting to be launched. The potential energy of the string is transferred to kinetic energy when it is released. That is then transferred into the projectile, giving kinetic energy and projecting it forward.
So for our sound and wave experiment, we're doing a dancing ping pong ball lab. And as you rub your finger around the rim of the wine glass, a sound is produced. This occurs because as your finger glides across the rim, it sticks due to friction, but then slides because of the water reducing friction. This action causes the glass to vibrate. A vibration from the glass pushes the air molecules around the glass, causing waves to form and compress. This is what makes the sound we hear.
Okay, wave defined is a disturbance that travels from one medium to another. There are two main types: longitudinal and transverse waves. Transverse waves travel up and down, longitudinal go horizontally. A wave is measured in wavelength. In a wave, there is a crest and a trough. A crest is the high point of the wave, and the trough is the low point of the wave. There is also something called a standing wave. A standing wave is when two waves converge to form one. The nodes are spots that stay the same and experience destructive interference. The antinodes experience constructive interference. These nodes, there needs to be a certain frequency to produce a standing wave.
And then for resonance, as we stated, the compressed air molecules around the glass are sound waves. As the waves begin to exit the wine glass, they come in contact with outside air molecules. The wave reflects off that air and begins to travel back to the wine glass. When traveling back to the glass, the sound wave collides with another wave on its way out of the glass. These two waves experience constructive interference and form a standing wave. This process is known as resonance, and as the waves resonate, you're able to hear the ping pong ball in the wine glass. And then Ryan is gonna get his finger wet and rub it around the rim. and the noise is produced and the glass is vibrating. So now we're going to turn it on its side and do the same thing. And the ping pong ball starts to dance because of the vibrations from the. So for our electricity demo, we are creating lightning, and to create the lightning, we used charge and static electricity. So as you rub the balloon through your hair, the electrons are moved. The flash of the light is static electricity. The static electricity you see is caused by the movement of the electrons. Electrons carry a negative charge, which causes protons, which are positive, to be attracted to them and repel from other electrons. When the balloon is rubbed through your hair, it either pulls electrons onto the balloon or strips electrons off your hair. This makes the balloon charged, meaning it either has more electrons or fewer electrons than protons.
Current and magnetism is also a factor in this. Electrical currents cause magnetic fields to form around them. Lightning strikes are rapidly moving electric currents, and the movement of electric charges induces magnetic field. One way lightning demonstrates magnetic fields is by creating magnets. As the storm cloud builds, it becomes polarized, which creates voltage where the protons and electrons want to join back together. As the charges are kept apart, the voltage between the protons and electrons builds and lightning strikes. As lightning hits the ground, charges flow down through lightning into the ground. This flow of charge is referred to as current. As you rub the balloon through your hair, the balloon becomes charged, and when the spoon comes in close contact with the balloon, a spark is created.